We'll be looking at question 20, June 2019 paper. In this question, which is about weak acids, you've got a table of 3 different weak acids, and you can see that you've got a range of different weak acids. What's interesting is the Ka value. Now you see the Ka value is H plus, and the rest of the weak acid, negative ion, over the concentration of Ha. What's interesting is the greater the Ka value, that means there's going to be more dissociation, and there's going to be the original concentration of the weak acid will decrease. So it just gives you an idea. So that means iodic acid is the stronger of the weak acids, and hydrocyanic acid is the weaker of the weak acids. And you've got propanoic acid in the middle. Anyway, that was just some general comments there. First question is asking, calculate the pH of this concentration propanoic acid. So what we'll do, we've got Ka is equal to H plus and the rest of the weak acid, and we make 2 assumptions: that the concentration of the weak acid remains virtually the same, so we can divide that by 0.0800, and that the negative ion produced has the same concentration as H plus. So we change that to H plus squared. And Ka is given to us from the table. We rearrange, we square root, and we work out the H plus concentration, and then we plug that into the pH expression, and that gives us the pH. So 1.35 times 10 to the minus 5 multiplied by 0.08. We're then going to square root that answer, and we're then going to plug that in to minus log to the base 10. That gives us, they want it to 2 decimal places, which works out to be 2.98. Yep, and the mark scheme supports that. Moving on. It's asking here, a student adds a total of 45 centimeters cubed of sodium hydroxide to this volume concentration of propanoic acid, this volume, this concentration propanoic acid, and monitors the pH throughout. Show by calculation that 20 centimeters cubed of sodium hydroxide is required. How do we work that out? So you see, for propanoic acid, we get its volume, convert it to decimeters cubed, multiplied by concentration. That gives you the moles. Which gives you 0. minus 1, minus 2, minus 3 moles. Now, this moles reacts in a 1-to-1 ratio because there's 1 H plus that's given off, which reacts with the OH minus. So for NaOH, we know what N is, we know what C is. We're trying to work out what volume is needed to neutralize it. So what we do, 0.002 divided by 0.100, and then multiply the answer by 1,000 to give your answer to centimeters cubed. Yep, 20. Good. Let's see how they do it. Yep, they did it the same way in the mark scheme. It says calculate the pH of the final solution. Okay, what we've got here, ladies and gentlemen, we've got propanoic acid reacting with sodium hydroxide. That's going to give you sodium propanoate and some water. And so what we've got here, we've got the volume and concentration of propanoic acid. We already worked this out, 0.002 moles. For sodium hydroxide, we got 45 centimeters cubed, 45 multiplied by the concentration. What does that give us? That gives us 0. minus 1, minus 2, minus 3, 5 moles. I'm going to put another 2 there just so that we can compare. And when the reaction takes place, all of the propanoic acid is going to get used up, and there'll only be 0.0025 moles left of this. And you'll get the equal amount of the salt. The salt will not affect the pH. That's 0.0020 moles. And you got water we can disregard. So really, it's the sodium hydroxide. So NaOH, we've got 0.0025 moles divided by the total volume. What's 45 plus 25? That's 70. So we divide the moles by the volume, which is 70. Convert it to decimeters cubed. This will give you the concentration of the hydroxide ions. 0.03571428 moles per decimeter cubed. And we use the Kw expression because this is an alkali solution. And Kw is 1.0 times 10 to the minus 14. It's given in your data sheet. H plus we're trying to work out. And hydroxide ion concentration is given what we just worked out. And then we plug the expression to minus log to the base 10 of H plus, what we work out there. So let's have a look. It's got a negative answer 1 minute. I think I forgot to put the negative in. Minus log to the base 10 of that answer. Yep, that's better. 2 decimal places, 12.55. It's worth 4 marks. Yep, the mark scheme supports that. Let's have a quick look where the marks are from. 1 mark is to work out the final moles of the excess sodium hydroxide. 1 mark is for working out this for the concentration. 1 mark is to work out the H plus concentration. So it's going to be, rearranging this expression, and 1 mark for the answer. Wonderful. Moving on. On the axis below, sketch a curve for the pH that changes during the reaction. We know that the end pH is about 12.55. 7, 8, 9, 10, 11, 12. 12.55. So at 45, it should be ending about here. We know that it neutralizes at 20. something like this. Because this is a weak acid and a strong base, the shape looks like this. If it was a strong acid, strong base, it would look something like this. But we're dealing with a weak acid, so you've got something like this. So this is worth 3 points for this curve. Where are those 3 points? Let's have a look. 1 mark for a slight rise. Actually, my graph should have been a little bit flat. So something like this. And then we got something like this. Yep, slight rise, and then near sort of almost vertical, and then a slight rise. Yep, the shape of the graph, that gives you 1 mark. The pH vertical section within the extremes of 5 to 12, minimum of 3. So we're looking at least, that's about from there to about there. 3 to 5, minimum 3 pH units, that's fine. Middle of the vertical section needs to be above 7. So the middle of it, which is about there, and the vertical section should be at 20 centimeters cubed. Yep, we get those 3 marks. Next, it says here, the student considers the 4 indicators. Explain which indicator is most suitable. Which one is most suitable? You see, ladies and gentlemen, we need to look at the pH range of this titration curve, and it's approximately between 4 to about 11, 4 to 11. So which of these fits in the 4 to 11 range? 4 to 11 range. Nope. 4 to 11, nope. The last one, 4 to 11, nope. Crescel purple, 4 to 11, yes it does. That range there and highlighted above there. So we say, which indicator would be the most suitable? With Crescel purple as the pH range of the indicator matches the vertical section of the pH range in the graph. Yep, putting that into words. Moving on. Still recording, I hope we are. Moving on. The student repeats the experiment, starting with, you've got the same volume and concentration, but you're using HCN and adding a total of, again, the same volume and concentration of NaOH. But this time, you're using HCN. Where's HCN? You're using HCN. So 6.17 times 10 to the... So what it is, we could do a quick calculation here. 6.17 times 10 to the minus 10 equals, the concentration of it is the same. So I'm trying to do this in my head. Just multiply that by 0.08. If we square root that, That will give us the H plus concentration, and the pH, therefore, will equal minus log to the base 10 of that. We've got 5.15. 5.15 pH. So what that's going to mean is, what's the similarity? So the starting pH should be around 5.15. Let's get a different color pen here. 5.15, you'll be looking around about here. So you see, what's the difference? The starting pH. The difference will be starting pH will be higher of HCN. That's going to be a difference. And the similarity, what's the similarity? The volume used for the neutralization will still be the same. And the end pH of the solution will also be the same. So you've got two options there. Volume of 20 centimeters cubed is the same. Or we could say final pH is the same. I hope that makes sense, ladies and gentlemen. I think we're on the last question here. The student calculates the pH of same concentration, but this time of iodic acid. Sorry, what's this called? Iodic 5 acid. The student assumes that the equilibrium concentration is the same as the initial concentration. The student measured the pH and finds out the measured pH value is different than the calculated pH. Explain why the measured pH is different. You see, for iodic 5 acid, when the dissociation takes place, it gives you this, and IO3 minus. You've got the Ka value. Why is the measured pH different? You see, because the Ka value is large, it's the larger value of all three, that means that the HiO3 is a stronger of the weak acid. So this concentration here is actually going to be lower than the initial amount. So putting that into words, it's got a large Ka value, meaning a stronger weak acid. It is. And additionally, you can, as an option, you can say that the concentration of iodic acid at equilibrium is lower than its initial. So this is another option to answer, but the first point made is sufficient to get this answer, to get this mark. Okay, ladies and gentlemen, that's the end of that. I will see you tomorrow.